So today let's move on to the heart of this subject, delay. Okay, so I have a CMOS inverter. This is WN, this is WP, and of course some channel length is there, right, but it's the same length. So going forward I will not keep mentioning this L, I will just drop it. That's assumed to be the minimum channel length at 2 lambda, we will just assume. Okay, and there is a load capacitor here. Okay, and my input is assumed to rise instantaneously from 0 to VDD. Okay, so what is the good model in order to find out how long it takes to go to the other state, and how do I model these two transistors in both cases? So it turns out that for output rising, the rising will happen through the PMOS transistor, right? And you remember that we calculated a resistance for the NMOS transistor when you discharge the capacitor, right? So similarly the PMOS will have a resistance R equivalent of P. Okay, this is my output Y. What happens to the NMOS transistor when you are rising? It will be off. Okay, similarly when the output has to fall, the PMOS transistor will be off, and it's going to get pulled down to ground through a NMOS transistor. And of course I have this load capacitor CL here. Right, this is my switch model. Okay, so earlier we said that okay, it doesn't matter what the size of the NMOS and PMOS transistor, widths of the NMOS and PMOS transistors are, the output logic level will swing from 0 to VDD, right? So does it mean that we don't have to worry about the sizes? Well, that's not entirely true, because when you come to delay, the delay indeed depends on the width of these two transistors, right? So how do I evaluate the fall delay? Output is falling, PMOS is turned off, NMOS has turned on, and what did we derive this expression to be? Yeah? Sorry? Yeah. So we basically said this was 0.693 into R equivalent of P into CL. Right? This is right. Now similarly, what's the rise delay? Is 0.693 R equivalent N into CL. No, you are right, this is N and this is P. Yeah. Okay. Now there is no reason to make the rise delay lesser than the fall delay, because in any general circuit both edges are equally important for me. When the input rises, I want the output to fall. When the input falls, I want the output to rise, but both should happen quickly enough. There are certain special cases like in memories, for example, where you might want to turn on the memory cell very quickly, but it's okay to turn it off slowly. In those cases, yes, the rise delay may be more important than fall delay. but in general, without loss of generality, it's the safest assumption to make is both edges are equally important and both delays should be similar. No reason to pick one over the other. Therefore, I would say R equivalent N equals P into CL, right? So, what was R equivalent N? 3 by 4 VDD by ID sat N, right? R equivalent P, you can check it out, is very similar, ID sat, yeah, ID sat N, ID sat P, right? So, I want these two to be the same, which implies that the charging current, effectively if you cancel out all the common terms, CL, VDD, everything, you will find that ID sat N should be equal to mod ID sat P, okay, leaving out all the sign there because I am just talking the magnitude of current here. Now for this to happen, you will find that if the technology is symmetric, VTN equal to VTP and all that, all these VDD minus VT, VD sat will all cancel out, right? All of those terms will simply go away and you will find that Kn prime Wn should be equal to Kp prime Wp, okay, I will say mod here. So what is Kn prime by the way? Mu n Cox Wn equal to mu p Cox Wp. Of course, you can cancel this out, which implies that Wp by Wn should be equal to mu n by mu p. This for equal rise fall delay. So typically this ratio is approximately equal to 2. Wp is twice Wn is the standard gate sizing that will be done in digital logic. You will see it everywhere because I want rise delay and fall delay to be the same, approximately equal. Of course, if your technology is very different, VDSAT, VTN, they are all very different, then you have to take ratio of the ID sats in order to find this appropriate sizing. Okay? Any questions here? So this 2 is a sort of a magic number that will be used. So just to clarify the sign convention, not the sign convention, the sizing convention. We say that the length is 2 lambda, right? So 2 lambda equal to technology node. So if it's 180 nanometer, it's 2 lambda is 180 nanometer. That means lambda is 90. If it's a 14 nanometer technology, then 2 lambda is 14 nanometer, right? That's the convention. Then typically this will be 4 lambda and this will length will be 2 lambda, this will be 8 lambda. Okay? So you will construct what is known as a reference inverter first. Okay? This reference inverter is what is going to give you the reference to size all other gates in your circuit later on. So for example, I might need an inverter with larger drive strength. So with twice the drive strength, then I'll just double both NMOS and PMOS widths, right? This reference inverter, it need not be that the width should always be 4 lambda and the PMOS width should always be 8 lambda. In some technologies, it could be, for example, this could be 8 lambda by 2 lambda and this could be 16 lambda by 2 lambda. The minimum width that is allowed for the NMOS, right, which is 8 lambda or 4 lambda, is determined by other factors in terms of manufacturability, in terms of variability and all that. In the end of this module, I will tell you, I'll try to give you a short primer on variability so that you understand why these arguments come in, right? But in a technology, they will find out what that minimum width is. That is, that you can successfully manufacture across devices, across wafers, and consistently give you the same current and same manufactured width. Then based on that, you will size the other guy to be twice that. Okay, so nothing sacrosanct about 4 lambda. Clear? Yeah. So let us now look at the transient response. Let me just tell you exactly what these delays are, this tau rise and tau fall that we just calculated now. Okay, so maybe I should just draw the inverter again. CL, V in, V out, and this is my WN, WP. Okay, so my V in, right, is initially assumed to be, in reality, by the way, let's just look at the real case, like this. My V in. V out, if V in is 0, what is V out? VDD. So it will start at VDD, okay. So let me just get this. It will start at VDD, and then it has to fall, right? Now question is, will it just start falling like this? What will happen? Huh? Huh? No, it will fall with a delay, yes. So I'm saying, yeah, it will fall with a delay. So maybe, yeah, I can draw it till here, right? And then is, or you want me to draw it more to scale, I can do that, so that, yeah. Is this how it will be? Why? Okay, fine. So if you remember, this is the VDD by 2 point, right? Now this is, so there is a delay, clearly, right? So I'm asking you, is that all that will happen? What are the capacitances now? Between the input and the output, is there any capacitance? Which capacitance is there between the input and the output? Yeah? Gate to drain of both NMOS and PMOS, right? Because remember, for both of them, this is drain, source, source. So there is a CGD which is sitting between input and output like this, right? Therefore, this cannot happen like that. As soon as this input rises, the voltage will not change instantaneously across that capacitor, the CGD capacitor. Therefore, this will go up slightly and then drop all the way down. Similarly, when this input falls instantaneously, this would go below ground, and then come up. Is that right? You agree with me or not? You don't. Why not? It's an instantaneous thing that it is going. Very instantaneously it will go to a small value, especially see later you will see that when the nodes are actually floating and is not being driven to a value either VDD or ground, this voltage can jump significantly above VDD. So you should do this simulation and see for yourself. The reason why this bump is there above VDD and below ground is because of this coupling capacitance between gate and the drain of both NMOS and PMOS transistors, right? So therefore, now where is, this was my 50% point for the input, this is the 50% point for the output. This delay is my tau fall. Similarly, this is my input here, output delay, tau rise. The delay from input going to 50% to output going to 50% is defined as the delay, okay? Input 50% to output 50%, okay? However, remember that the expressions that we derived earlier, 0.693 R equivalent into C, was assuming that my input went instantaneously from 0 to VDD. This was the assumption that we made, right? So if you look at that delay, I mean that case, the delay would happen earlier, like this. So it turns out that by dropping that 0.693, we can capture this actual delay case where the input itself is rising a little slowly. Input, when it has a finite rise time within reasonable limits, then the output will, take slightly longer. How much longer? It turns out that if you drop that 0.693 R equivalent into C, that's a fair estimate of the delay, and therefore we will simply say that this is equal to R equivalent N into CL, and this is equivalent to R equivalent P into CL. Henceforth, we will not put 0.693 in our delay expression for this reason. Okay, it's only an approximation, it's not true really, but anyway we are only looking at back of the envelope calculation estimates, right? Ultimately what what is the, we have derived quite a few expressions till now, so it's important to understand where we intend to use them. I am not, for example, trying to use these expressions of delay and other things to figure out if inverter A is 5% faster than inverter B. That I can never do, because the actual current model is so much more complex. I can never capture all that in my equations here, in these back of the envelope calculations. But with these expressions, I can always tell you if inverter A is 50% faster than inverter B, or maybe 30% faster. That level of estimate I can give you with these back of the envelope calculations, where we have simplified the model, got an understanding, we get some delay estimates. I can tell you, yes, this configuration is going to be at least 30% faster. Whether it is 27% faster or 33% faster, you have to do a simulation. Okay, that is the philosophy of these derivations that we are doing. So now if you ask me, is that 0.693 necessary? Well, honestly, in both inverter A and inverter B, if I drop the 0.693, it doesn't matter. I am only looking at telling you which one is faster. and even the 30% faster will still hold even if I drop the 0.693, right? Keep that in mind for all the derivations that we are doing throughout this. Ultimately, you have to resort to simulation for accurate estimates. No choice there. Okay? So, any questions on delay? Yeah. No, the true. Correct. No, no, no. See, the voltage cannot change instantaneously across a capacitor, right? So the C dV by dt you cannot have an instantaneous change, which means that there is an infinite current otherwise. Correct. So to maintain that, the other end will also follow the input for a short while. Right? This is a sort of a very high frequency switch that's happening when the input changes instantaneously. Therefore, it will, the other plate of the capacitor will follow this node a little bit, and that's why that initial bump is happening there. No, no, that's why it's not following exactly. It's not, for example, this node is just not going up like this, right? The input is actually going all the way to VDD. That's not happening. It just that momentary thing, it will go, and then of course the other NMOS, now the NMOS transistor turns on, and so therefore it will fall. So there are multiple effects happening there, right? One is the capacitor which is causing this coupling. Other is the NMOS transistor is now turning on. So now that will take on and then pull that node voltage down, right? However, if it was not, if the NMOS did not turn on, let's say, okay, in this process, then this node voltage would jump to a much higher value, and it would actually remain there after that. It can remain at a value much higher than VDD after that, because nothing is there to pull it down. This is what I meant when it's called a floating node. I'll come to this later. Okay, you will see this happen in your simulations also. Okay? Yeah. No, no, no. So we have lumped all the capacitances as CL for now, actually. Later, I'll show you how we are going to account for all these capacitances. It does come into the picture. Yeah, actually it's just a representative capacitor for now. I'll tell you what these elements are when I move on into the course. Yeah, so see, what I said was, when we did that 0.693 derivation, the assumption was V in went from 0 to VDD instantaneously. Okay, now you leave all this output, rising and all that, forget all that. Output will now fall like this, right? So this delay we said was 0.693 R equivalent into C. Now what am I saying? I am saying the input itself is rising slowly. That means the output is actually going to take that much longer. Now I have run out of colors because someone told me that green is not visible from there, so I'll use black. So this output, when with the magenta input, where the input is rising slowly, will take longer, right? So in that case, the delay is actually from here till here, and it's longer delay. How much longer? 1 by 0.693 times longer is all we are saying. So this we are saying is approximately R equivalent into C. Output? Correct, in the sense you are right. So here the you are saying that somewhere here is VTN, and only then it will fall. Correct. So what will you're right. So what will happen is, until VTN, that capacitor will be floating, in the sense the output will just follow the input. Then the NMOS turns on, then it will start dropping. You're right. So again, it's too cluttered for me to show all of that here, but you're right. You have to look at the point at which, at VTN, up to VTN it will follow, output will follow the input and then start falling. Any other questions on delay? Okay.